A Chinese car company just built an engine that gets 106 miles per gallon. Guinness World Records flew in, tested it on a real road, and made it official. That is not a typo. It is not a sleek concept car sitting behind velvet ropes at a futuristic auto show. It is a real production vehicle rolling off an assembly line right now. A car that could theoretically carry you from New York to Chicago on a single tank of gas and barely dent the fuel gauge. To understand just how radical that number is, consider what stands in American driveways today. The average new car sold in the United States gets somewhere between 28 and 35 miles per gallon. The Toyota Prius, the vehicle that spent 25 years as the undisputed global symbol of fuel efficiency, maxes out around 57 miles per gallon in the city. 106 miles per gallon is nearly double that benchmark. And the company behind this achievement is not Toyota. It is not Honda. It is not Ford, General Motors, or Tesla. It is a Chinese company called Geely. If that name sounds unfamiliar, it will not be for long. Because the story behind this engine is not just about fuel economy, it is about a massive strategic blind spot that left Western automakers exposed. While Detroit and Silicon Valley spent hundreds of billions of dollars locked in an all-or-nothing war over pure electric vehicles, engineers in China were quietly solving the exact mechanical limits that have held gas engines back for over a century. The man who funded this breakthrough started his career with $3,000 in borrowed cash and a small shop making refrigerator parts. The engine his team built reaches thermal efficiency levels that Formula One teams spend billions of dollars trying to touch. And the technology inside it is already moving quietly toward American driveways through vehicle badges you see on the highway every day. By the time this story unfolds, you will see why the transition away from gas cars is not happening the way anyone predicted, and why the biggest disruption to the global auto industry was not an electric car at all. To understand how this record-breaking engine happened, you have to look at the man who built the empire behind it. His name is Li Shufu. He was born in 1963 in a quiet farming village in Zhejiang Province, China. He grew up in a world where almost nobody owned a private car, let alone dreamed of building one. But Li was obsessed with how things worked. In 1986, at 23 years old, he borrowed roughly $3,000 from his family. He did not launch an auto company. He opened a tiny workshop making basic components for refrigerators. It was simple, unglamorous manufacturing work. But it taught him how to manage supply chains, control costs, and build a factory from scratch. By the early 1990s, he shifted into manufacturing motorcycles. Then, in 1997, Li made an announcement that caused industry veterans to laugh out loud. He declared that his company Geely was going to build passenger cars. He had no background in automotive engineering. He had no established car factory, no state backing, no global partners, and no prestige. When critics pointed out how impossibly complex modern car manufacturing was, Li famously brushed them off, describing a car as nothing more than 4 wheels, an engine, and 2 sofas. The industry wrote him off as an amateur, but Li kept moving. By 2001, Geely secured a formal license, becoming the first private company in China allowed to build automobiles. That milestone was impressive, but Li was thinking far beyond domestic sales. In 2007, he sent a cold letter to Ford Motor Company offering to buy Volvo, the legendary Swedish brand famous for safety and European engineering. Ford did not even bother to reply. Undeterred, Li showed up at the Detroit Auto Show in 2008 and tried again in person. Ford executives brushed him off a second time. He came back in 2009 with a sharper team, deeper financing, and undeniable persistence. In 2010, the global automotive world watched in shock as the former refrigerator parts maker walked out of Ford headquarters holding the keys to Volvo, purchasing the brand outright for $1.8 billion in cash. Western analysts warned it would be a disaster. They predicted a Chinese startup would ruin Volvo's reputation for quality. Instead, Li gave Volvo's Swedish engineers the funding and freedom they needed, turning the brand into a wildly profitable global power. He did not stop there. In 2018, Li quietly acquired nearly 10% of Daimler, the parent company of Mercedes-Benz, instantly becoming the single largest individual shareholder in one of the most prestigious luxury brands on earth. Today, Geely Group controls Volvo, Polestar, Lotus, Zeekr, and major stakes in several global partnerships. The farmer's son who started with $3,000 now sits at the center of a global industrial web. And that relentless, practical ambition is the exact mindset that produced the engine now making headlines across the world. Before looking at the mechanics of Geely's new engine, we have to look at the massive consumer problem it was built to solve. For the past 5 years, the global car industry operated on a single, aggressive premise. The future belongs entirely to pure electric vehicles. Government mandates were passed, automakers pledged hundreds of billions of dollars to phase out gas engines, and advertising campaigns promised a seamless, zero-emission world. For millions of drivers, pure electric cars are genuinely incredible machines. They offer instant acceleration, whisper-quiet cabins, and the convenience of charging at home overnight. But as EVs moved from early tech adopters to everyday mainstream buyers across America, serious friction points began to surface. The first issue is public charging infrastructure. The idealized vision of pulling up to a fast charger, plugging in effortlessly, and leaving in 5 minutes rarely matches real-world road trips. Fast charging often means hunting down working stalls, dealing with broken payment apps, and waiting 20 to 40 minutes just to get a battery back to 80%. On a long family drive, that isn't a minor pause. It is a major disruption to a travel schedule. Then comes the impact of cold weather. Lithium-ion batteries are deeply sensitive to low temperatures. When winter temperatures drop below freezing across states like Michigan, Illinois, or Minnesota, an electric vehicle can lose anywhere from 30 to 40% of its advertised range. A driver who paid for a 300-mile EV can find themselves staring at less than 200 miles of real-world usability on a freezing January morning. The heater runs, the battery cold soaks, and range anxiety becomes real. There is also the financial shadow of long-term battery degradation. While EV batteries come with multi-year warranties, out-of-warranty replacements can cost anywhere from $10,000 to over $20,000. For a used car buyer down the line, that potential repair bill turns an aging EV into a financial gamble, impacting residual values across the industry. Underneath all of this sits the electrical grid itself. The Department of Energy has repeatedly noted that widespread EV adoption requires massive, expensive upgrades to local power grids, transformer substations, and high-voltage transmission lines. Upgrading national infrastructure takes decades, not months. These challenges do not mean electric vehicles are a failure. They simply mean that for millions of suburban and rural drivers across America, switching to a pure electric car today requires real compromises in convenience, flexibility, and cost. This created a massive, unaddressed opening in the global auto market. Automakers in Detroit and Europe largely treated hybrid cars as a temporary bridge technology, an old idea to be phased out as quickly as possible. But engineers in China saw an entirely different strategic play. They asked a simple question: what if, instead of forcing every driver to rely immediately on an unfinished charging network, you created an engine so radically efficient that it eliminated range anxiety entirely, cut fuel costs down to almost nothing, and worked with the gas stations already standing on every corner in America? That is the exact gap Geely targeted, and the solution they built sent shockwaves through Tokyo, Detroit, and Stuttgart. To understand why Geely's new powertrain caused an immediate stir among automotive engineers, you have to look past the marketing claims and look at a single metric: thermal efficiency. It sounds like complex textbook jargon, but the concept is remarkably simple. Inside any gasoline engine, controlled explosions happen thousands of times a minute. Chemical energy in the fuel is converted into heat, and that heat expands to push pistons down, turning the wheels. But no internal combustion engine converts all of its fuel into forward motion. Most of that energy is wasted. It escapes as raw heat through the exhaust pipe, gets absorbed by the engine block coolant, or is lost to mechanical friction between metal parts moving against each other. Thermal efficiency measures the exact percentage of heat energy from burning fuel that actually turns into useful physical work to propel the car. For over a century, gasoline engines have been notoriously wasteful machines. The average gas-powered car sitting in American traffic today has a thermal efficiency of around 30 to 35%. That means out of every dollar you spend at the gas pump, roughly 70 cents is instantly lost as wasted heat radiating into the surrounding air. For decades, pushing that efficiency number higher was considered one of the hardest engineering problems in mechanical physics. When Toyota launched its dedicated hybrid program, their engineers spent years refining the combustion chamber, gas flow, and compression ratios. They eventually achieved a thermal efficiency of 41% in their Atkinson cycle engines. That single achievement is the primary reason the Toyota Prius became the global benchmark for fuel economy for more than 2 decades. Reaching 41% was treated across the industry like reaching the peak of Mount Everest. Most experts assume production engines were very close to their physical limits. To put what happened next into perspective, look at Formula One racing. Formula One power units are the most expensive, obsessively engineered internal combustion systems ever constructed by human beings. Global racing teams spend hundreds of millions of dollars every single year trying to extract tiny fractions of a percent in performance, reaching thermal efficiency levels around 50% using custom exotic fuels, specialized energy recovery systems, and handcrafted components. Then, Geely stepped onto the stage at the Beijing Auto Show with a regular production engine named the BHE-15. It is a compact 1.5-liter four-cylinder engine designed for everyday family vehicles. But when independent testing agencies and Guinness World Records audited the engine, the certified thermal efficiency reading came back at 48.41%. That is not just an incremental improvement over standard passenger cars. That is within striking distance of a multi-million-dollar Formula One racing engine built into a mass production power unit designed for everyday commuter traffic. Geely achieved this by rethinking how fuel burns inside the cylinder. They used an ultra-high tumble intake port that swirls fuel and air into a precise cyclone, allowing the mixture to burn faster and more completely than traditional designs. They pushed the compression ratio higher, applied low-friction diamond-like carbon coatings to the cylinder walls, and used an advanced electronic variable displacement oil pump to eliminate internal drag. Connecting it all is an artificial intelligence control system that constantly recalculates ignition timing, valve opening, and fuel injection down to the millisecond based on real-time driving conditions. The engine never works too hard or wastes a drop of fuel. It operates constantly in its absolute sweet spot, squeezing every available joule of energy out of the gas inside the chamber. It is a mechanical achievement that effectively redefines what a traditional engine can do. An ultra-efficient engine sitting on a laboratory test bench is an impressive engineering achievement, but its real importance only becomes clear when you bolt it into a production vehicle and drive it onto an open highway. Geely took this record-breaking 1.5-liter engine, paired it with a high-output electric drive motor, and installed the system into a full-sized family sedan called the Galaxy Starship 7. To verify their efficiency claims under strict, standardized conditions, they brought in official adjudicators from Guinness World Records to conduct a certified long-distance drive. The test recorded an average fuel consumption figure of 2.62 liters per 100 kilometers. Converted into standard American measurements, that translates directly to 106 miles per gallon. To see what 106 miles per gallon actually looks like in everyday life, consider a standard road trip across the United States. A typical modern gas-powered sedan carries a 15-gallon fuel tank and averages roughly 30 miles per gallon, giving the driver a real-world range of about 450 miles before needing a gas station. At 106 miles per gallon, that same 15-gallon fuel tank delivers a total driving range of roughly 1,590 miles on a single fill-up. That means a driver could start in Los Angeles, cross the desert highways, navigate through the Rocky Mountains, pull into Denver, turn around, and drive almost all the way back to California without stopping at a gas pump a single time. Or consider a drive up the East Coast. You could fill your tank in Miami, Florida, drive through Georgia, the Carolinas, and Virginia, pass Philadelphia and New York City, and arrive in Boston, Massachusetts on one single tank of gas. In 2024, Toyota staged a highly publicized drive with a purpose-built Prius, traveling from Los Angeles to New York to showcase their best modern hybrid capability. Across the entire cross-country trip, the vehicle averaged 93.1 miles per gallon, setting a baseline record that made global automotive headlines. Geely's new production system cleared that number by over 13 miles per gallon. What makes this shift even more critical for global automakers is that Geely is not acting alone. Across China's auto sector, a hyper-competitive hybrid war has broken out. BYD, the Chinese manufacturing giant that recently overtook Tesla in total global electric vehicle production, released its fifth-generation hybrid platform, delivering a certified 46.06% thermal efficiency and a total driving range exceeding 1,300 miles on a single tank and charge. Rival manufacturers like Changan, Chery, and Great Wall Motor have all introduced production hybrids capable of clearing 1,200 miles of real-world driving. While legacy automakers in Detroit and Europe spent years treating hybrids as a legacy technology, Chinese engineering teams turned them into high-tech, ultra-efficient range platforms. The gap between a traditional American gas engine operating at 35% thermal efficiency and a hyper-hybrid operating near 48% is not a small product update. It is a generational leap in how energy is used. And for legacy auto brands operating on traditional margins, that engineering gap represents an immediate threat to their market share. The immediate question for American drivers and industry executives is simple. If these vehicles are being engineered in China, why should Detroit, Silicon Valley, or drivers in North America care? The answer lies in how modern corporate ownership works behind the scenes. Geely is not just an isolated domestic brand operating inside Chinese borders. Through the expansive corporate network assembled by Li Shufu, Geely owns and operates brands that are deeply familiar to Western consumers. They own Volvo, they own Polestar, they own Lotus. They hold a 50% joint venture with Mercedes-Benz to manufacture smart vehicles, and they remain the single largest individual shareholder in Mercedes-Benz's parent company. More importantly, Geely recently formed a joint venture called Horse Powertrain alongside European automaker Renault. This global powertrain enterprise was created specifically to design, manufacture, and license ultra-efficient internal combustion engines and hybrid systems to third-party car brands around the globe. That means this 106 miles per gallon engine architecture is not going to stay locked inside Chinese domestic models. The underlying engineering, thermal management software, and hybrid systems are actively being integrated into Volvo's upcoming vehicle portfolio, Polestar's product roadmap, and shared platforms across Europe and international markets. In the coming years, American buyers walking into local dealerships will see sleek, highly efficient hybrid crossovers and sedans carrying familiar European safety badges. Underneath the hood, powering those vehicles through sub-zero winters and cross-country highway drives will be the high-efficiency powertrain technology developed in Hangzhou. It represents a quiet re-architecture of the global car market. For the average American consumer, this technology lands as a welcome practical solution. A vehicle that delivers over 1,000 miles of driving range per fill-up solves the immediate financial sting of high gas prices without forcing a driver to deal with cold weather range drops or search for rare public charging stations. You simply fill up once a month, drive wherever you want, and use a fraction of the fuel consumed by standard gas cars. For legacy automakers in Detroit and Tokyo, however, this shift represents a serious strategic reckoning. Major car companies spent the last decade making a high-stakes choice: put almost everything into pure electric vehicles or keep relying on legacy gas engines that haven't fundamentally changed in years. By treating hyper-efficient hybrids as an afterthought, traditional brands allowed competitors to take a massive lead in the exact bridge technology that regular car buyers want right now. The transition away from traditional gas cars was supposed to be a slow, predictable changeover controlled entirely by legacy automotive giants. Instead, a farmer's son who started out making refrigerator parts re-engineered the internal combustion engine, pushed thermal efficiency close to Formula One levels, and proved that a regular car can run over 1,000 miles on a single tank. The global race for the future of driving is no longer just about who can build the biggest battery. It is about who can squeeze the most work out of every single drop of energy. And right now, the rules of that game have been completely rewritten.